In this video, we're going to talk about blue shifts and red shifts. So here we have an animation of a yellow star moving towards us and away from us, associated redshift and blue shift spectrum, and the speed of the object toward us and away from us. Here's the spectrum. Here is the radial velocity plot, which has speed on the vertical axis and time on the horizontal axis. And over on the left is an animation. Now you're over here looking towards this face-on or edge-on plot. Now on the edge-on, we have this blue planet that is orbiting around the yellow star. And you're looking at it in the edge-on view. If you're looking at it in the face-on view, you can see the blue planet is orbiting around the yellow star, and the yellow star is orbiting around a common center of mass. Now, in this particular example, we see one set of spectral lines, which are the dark black lines. They're the absorption lines. And because we only see one set, the dark lines, there's only one object that we're getting the lines from, and that is this yellow star. We cannot see this blue planet in the orbit around the yellow star. The only light we get is this yellow star that is orbiting around the common center of mass. Now, the light that's being emitted in the lab is these dash lines that you can see. So in the lab, we have a gas or gases, and they're being emitted, but the gases are not moving. And so you see the dash lines at the exact same wavelengths of how they would appear in the lab. But because the star is moving towards us and away from us, towards us and away from us with these speeds coming towards us and away from us with speeds of 10 meters per second to minus 10 meters per second, we see these spectral lines shifting towards the red side of the spectrum, then the blue side, then the red side, then the blue side. So what you get from observations is these spectral lines. And if over time, which the horizontal axis is, if over time the lines appear to cyclically shift towards the red, towards the blue, towards the red, towards the blue, that tells us that we are looking at a binary system, at least a binary system. Could be a triple system or quadruple, but in this particular example, it's a binary system. So something must be causing this yellow star to wobble backwards and forwards, wobbling away from us and towards us. So we infer this planet to be in orbit around this host star. And this is one of the ways that we find exosolar planets or exoplanets. This technique is called the radial velocity technique. So here, if you look very closely, when the object of the star is moving towards us, away from us, towards us, and away from us, you'll see when the star is moving towards us, you get a blue shift, and when the star is moving away from us, you get a red shift. Shift to the blue is a blue shift, shift to the red is a red shift. A blue shift is when the star is moving towards us, and a red shift is when the star is moving away from us. So we see cyclically changing blue shifts and red shifts, blue shifts and red shifts. And the amount of shift is based on this wavelength change from the stationary position. And we relate that to the speed of the object coming towards us and away from us, which in this case, this host star is moving at a maximum speed of 10 meters per second towards us and away from us. This is what we mean by redshift and blue shift spectrum of an animation of a star moving towards us and away from us, generating a radial velocity plot that is used to find or infer an exoplanet in orbit around its host star.